All right, we're back to Eng Maths. I've talked about distributions. Please don't forget this. I've talked about distributions, I've talked about statistics. It's time to talk about differential equations again. Okay, so this thing with the partial differential equations, and which tends to come up with in the vibrating objects situation, apparently. Every semester, well, every year, only happens once a year, every year it's a cause of some pain to you and the Maths Learning Centre, because it causes you pain, it causes us pain. So I have discovered that there are very few actual examples of this, of what to do in those situations where, well, basically you don't know what to do. So the lecture notes seem to have quite a good amount of information about how to get started on it, but not all that much information about how to finish it off. Is that how people feel? Because that's how I feel. Yeah. So, yeah. Just give me a minute. All right, I'm just going to pick one and run with it. Maybe I'll get one out of the great big book of everything. Or do you want me to do that exam one? I may have to change the question when I get to the end. Okay. Something like that. It's a good one. And maybe no. Just give me a second. How do you pronounce these dudes' names? Is it Sturm? I always think it's like Louis Sturmville or something. 234. So you get to see now David's approach to studying things that he doesn't know very well yet. Oh, that's the Sturm-Louiville problem. Just that. As opposed to the PDEs, which use that. Ah, okay. I get it. Finally. Finally. Okay. I can tell you about that. Just give me 1 second. Yes. I'm just, damn. Why do these things have no actual questions to solve? Yeah, it's all right. All right. I will do the Sturm-Louiville. I know what I'm doing now. Okay, so the Sturm-Louiville problem is important because it comes up when you attempt to solve differential equations like this. Okay? There's usually initial conditions of some sort that have to do with this being 0, the function u being 0 at certain spots. So usually it's something along the lines of u like like no, I need an example, sorry. I don't know enough about this to come up with ones on my own. I'm sorry. Okay, I'm going to do this and see what happens. I would prefer to do one like it that's in the Maple TA, but if someone has one of those sort of on a screen like handy, I could look at it. I won't do yours. It may randomly end up being someone else's. Only for the purposes of the recording, I'm not really doing people's Maple TA for them, just, you know, anyone who might be listening in the future. I'm doing an example that is mildly similar. Go. And where? There. That is an 8. It's now an 18, so you can tell. Hello. Okay, I've come up with some answers, some questions. Okay. The reason the Sturm-Louiville problem is so important is that it comes up when you're solving these sorts of things. And it's a classic exam question thing to do the Sturm-Louiville bit for you. So I'm going to do that part of this and the other part of this, and hopefully now we'll have 3 examples of this on the Maths Learning Centre website. And maybe next year I'll get better at just emailing everyone when it comes up and saying, just check out these examples, people. So, all right, this is where we are, and we're going to attempt to solve this, and it has multiple very important parts. And your textbook, though this is like an older version, but you know the maths hasn't changed that much. Your great big book of everything splits it into various pieces, and there's a few very clever tricks that go on during the process, and there are a couple of nuanced what to do in various situations, things that will come up as we go on later that I will try and specify when we get there. Okay, so the first step is to assume, well, suppose that the solution for u is made out of multiplying something for x and something for t. Now, I'm just going to ask something. Your lecturer, do they normally call it capital F and capital G, or do they normally call it like capital X and capital T, or what? Okay, so they name it as the capital version of the variable that it belongs to. Okay, I'll do the same. You can call it whatever you want, but I'm just trying to make it more familiar to you. Like that? Okay. Right, that would be useful because then it would remind you what variable goes with what, what function goes with what variable, and that would be kind of very helpful. Okay, so this is my initial step, and my idea is that I'll differentiate this and sub it back into the original and see if that helps, which it will, because the wisdom of our forefathers tells us that it does. And so we'll go. If we differentiate this with respect to x, then anything involving a t counts as a constant. And so the derivative with respect to t, so not with respect to t, anything involving a t counts as a constant. Anything that's a constant is still there when if it's multiplied on, it'll still be there afterwards when we differentiate. So the t will still be there, and I'll differentiate this with respect to x, and I'll get that. And then I'll get d squared u on dx squared. And I'll differentiate, the t will still be there because it's a constant multiplied on, and I'll differentiate that again. And similarly, I could do that with my differentiating with respect to t. So du on dt equals, well, the xx counts as a constant, and the t will get differentiated, and the d squared u on dt squared. The xx still counts as a constant, and I'll differentiate that again. So something to point out that might be different in some other situations. This original equation involves a d squared u dt squared and a d squared u dx squared. It may be that one of them is just du on dx. Okay, there might not be squares in it, in which case you wouldn't differentiate it twice, you just leave it once. I'm trying to point out some differences that might happen. Or it might be like this past exam question here, where there's both a du squared on dt squared and a du on dt, and you'll need both of them and have to sub them both in. Okay. But I'm going to sub that in now and see what I get. So the original equation was d squared u on dt squared is 49 d squared u on dx squared. And so I'll sub everything in. The d squared u on dt squared is this, x t double dashed. And the d squared u on dx squared is x double dashed t. If it's okay, I'm going to leave out the actual variables, little x and little t, because I can remember that they are there because I've labelled my functions as the capital versions of those things. All right. And what I'm going to do next is sort of foreshadowing the very clever trick number 1. So what I'm going to do is it's called separation of variables, this method. And it's not just that I separated the x and the t into their own functions. That's the first way that it's separation of variables. It's also separation of variables because I'm going to separate these variables and put all the x's on one side and all the t's on the other. So that's the second time we're going to separate the variables. First we separated them here into their own functions, then we separated them here. Now that 49 is going to have to go somewhere. And I have to decide whether it's going to live on the same side as the x's or the same side as the t's. And so there's a decision to be made. It's very important when you're watching people do examples that you notice when they made a decision. Maths lecturers are not always that good at telling you when they made a decision. So here is a decision. We're going to have to decide where the number goes. So there's going to be one side of that is going to be just variables, and there's not going to be any numbers or minuses, and the other side is going to have a number, and we have to know where that is. So how are we going to tell? We tell by looking at this, because we're about to use this information. We're going to be making a differential equation that only involves one variable. Only involves one variable. And we know how to solve differential equations that only involve one variable, but we have to have initial conditions to be able to do it. Right. These initial conditions here involve subbing in a particular value of x and getting a particular value afterwards. These conditions involve subbing in a particular value of t and getting a function of x afterwards. These are not going to be particularly helpful for solving this equation because it's going to give me functions coming out. And I would much prefer to have homogeneous equations that don't have random functions everywhere. So these are the ones I want to think about. And these ones involve subbing in a value for x. So since these involve subbing a value for x, I'm going to make it so that the x's are all by themselves without another number. Okay? Sub in values of x, get number. That's my decision. So the boundary initial conditions are sub in x get number, in particular get 0, and so therefore I'm going to put the x's all by themselves. That's my decision. And I'm going to put the double dashes on the top. So I'm going to put the t dashed here, divide by the t and by the 49, like that. There's a really good reason for me to do that. It's going to make my work easier. And the other really good reason to do that is that when your lecturer does this part of the problem for you that is coming after this, it will usually make specific reference to one of the functions. So in this one, that may or may not be in the Maple TA, he makes reference to an x. And he solves that part for you. He says these are the eigenfunctions. The ones with the eigenfunctions need to be all by themselves. So if the lecturer does a bit for you where they find the eigenfunctions and eigenvalues, you need to arrange it to be by themselves. There's some decision-making processes for you. All right, here is clever trick number 1. This is a function of t, and it doesn't have any x's in it. This is a function of x, and it doesn't have any t's in it. But they're the same function. So whatever this function is, that these two things are the same function of, whatever this function is, that function doesn't have any x's in it, and it doesn't have any t's in it. And the only way you can do that is if it's a constant. For some k. I like to put the k in the middle to remind myself that it's equal to both of these things. That's clever trick number 1. It's not, doesn't look very clever when you read it, but that's where it comes from. Okay, so I need to figure out which k's make that work. Only some k's are going to work. Now there are, in fact, every possible k, every infinitely many real number k's will make this work, but only some of them will match my initial conditions here. Okay, so the first one I'm going to do is the one that doesn't have any other numbers floating around. The only number in here that's not an x is a k. And it's not so much that it's the x that I'm focusing on, it's the fact that it's the one that has the boundary conditions where you sub it in and get a number, those ones. That's why I've chosen x. Okay. So I have that x double dashed over x equals k, so x double dashed equals kx, so x double dashed minus kx equals 0. Don't technically need to do all of that, but that's the traditional way of writing it. Some people will write a lambda in this spot here. The reason it's called lambda is for the same reason that with matrices there's a lambda there when you do eigenvalues. When you multiply a vector by a matrix and you might get, ax lambda x, that lambda is an eigenvalue. In this case, instead of multiplying by a matrix, what we've done is a derivative. Derivative of x equals lambda x. That's why it's an eigenvalue. Derivatives act upon functions in the way that matrices act upon vectors. It's very cool from an algebra point of view, and I think it's just awesome. I drool when I learned it, and I didn't even do differential equations. I did algebra 2, and I went, derivatives is a linear transformation. Okay, and then I had to do Sturm-Louiville, and the wonder went away. Anyway, that's why it's called an eigenvalue, and you'll find that they will tend to call it lambda when they do this. Problem is that we've already used lambda when we did differential equations, with constant coefficients, and my lambdas are going to get mixed up, which is why I'm using k the way I did in the lectures. But be aware that sometimes they'll put a lambda in that spot, and you'll have to keep track of the fact that if you're using a k, it's really a lambda. All right. Nothing like them changing the letters on you to confuse you when you really know you shouldn't be confused, because you can choose whatever letters you want, but then it turns out you're confused anyway and you kick yourself. So this is where we're up to. This is, ready, this is a linear differential equation with constant coefficients. That's what this is. The only difference between this and my ordinary linear DEs with constant coefficients is that I don't know what the constant actually is. Normally, if there was a 2 there, I'd be great. X double dash minus 2x, I could turn that into a characteristic equation and go from there, and I'd do my e to the root 2 and my e to the minus root 2, and everything would be happy. The thing is that I do not know what this k is, so I'm going to have to run through all the possible things that k could be. That's my next stage. So my possibilities for k are that k equals 0, or k is positive, or k is negative. They are my possibilities for what k could be. And I'm looking for non-zero solutions. So I'm looking for a function that is not always 0, that sometimes when I sub in x it doesn't give me 0. And the other thing is that, well, I know that x being 0 will work perfectly well. 0 minus k times 0 is totally 0 double dashed is still 0, and so 0 minus k times 0 is always 0, so I don't need the 0 solution because I've already got it. Okay, I'm going to run through each of these possibilities. K equals 0. Okay, when k is equal to 0, I get... Damn, I should have done something first. Sorry about that. The characteristic equation is lambda squared minus k equals 0. Lambda squared equals k. That's why I don't like to use lambda here, because normally you use lambda when you do a characteristic equation for a second order linear DE with constant coefficients. Your alternatives are to use k and lambda, or to leave this as a lambda and use some other letter here, whatever. Right. So when you get a linear DE with constant coefficients, you put the double dash ends up being a lambda squared, the single dash is a lambda, but there isn't one. And the original function becomes just a constant, and so we end up with that. And when I solve that, I get lambda squared equals k. I am not going to finish solving that at this stage, because depending on what k is will change how many answers there are. So if k is 0, then I've got lambda squared equals 0, which means that lambda is 0 twice. And when you get 0 twice, the repeated root, the solution will be constant e to the lambda x plus constant x e to the lambda x. You don't need to put in all those 0 x's, but I find it helpful. And so that becomes a plus bx, because e to the 0x is 1. Okay, I'm using something from Maths 1b here, where whether you get repeated roots or different roots or imaginary roots give you different solutions to the differential equation. So this is where I am here. Now here's the thing. I don't know, I mean that's a solution. A plus bx, if I differentiate that, if I put that back up to the thing there, it will actually work. If I have a plus bx and I sub it back into this here, it will work, it will come out to 0. Problem is that it might not match these initial conditions over here. And these initial conditions over here, they involve t. I'm going to have to deal with that because there's no t's here. I made the t's go away. Damn, I forgot something. I'm going to have to put it back in. Luckily, I'm using paper that isn't connected to itself. You may have a harder time. Well, no, that's okay. I'm going to need initial conditions. So I know that u x 0t equals 0, and ux is du on dx. And so that's, I've got that, du on dx is x dashed x t, because that's what du on dx is. But the x is 0. And that comes out to 0. But this is supposed to always be 0, no matter what little t is. For any little t. So since I'm looking for non-zero solutions, the capital T sometimes, either capital T is always 0, which I know is not true, which means that if this is sometimes not 0, I can divide by it, which means that x dash 0 is 0. That's what I've got there. I also have that ux 2 pi t is 0, and that's going to be x dash 2 pi t like that. And this is supposed to be true no matter what t is. So again, since this is true for every possible little t, including when it's not 0, I can divide by that and get x dashed of 2 pi is 0. So I've got my initial conditions now. Let's have a look at what that means. I'm up to a plus bx, and I have these initial conditions. X dash 0 is 0, x dash 2 pi is 0. Okay, so let's see. X dashed is b. Great. So just differentiating that. So x dashed of 0 is still b, and according to my initial conditions, that's supposed to come out to 0. So b is 0. And so therefore x is not a plus bx, it's just a. Alright? There we go. Unfortunately, my other initial condition is not going to tell me what a is, because the other initial condition is also about the derivative. If, on the other hand, it had said just x of 2 pi is 0, then I would have get, well, x of 2 pi is still a, which is 0, and a and b would both be 0, and I'd just get, well, that the capital X is 0, which means I haven't found a non-zero solution. But I have found one here. The a could be non-zero. That's a solution. K is positive. Okay, if k is positive, I'm going to get lambda squared equals k, and I'm going to have to square root it. And since I'm going to square root it, I might as well say that k is something else squared. Traditionally, and I don't know why, mu, perhaps because it's the letter after lambda in the Greek alphabet. Okay, so let's see. Lambda squared is mu squared, and lambda equals plus or minus mu. I am going to specify that mu is positive, so that when I talk about the plus or minus mu, it's a bit it's unambiguous. Okay, the wheat, which means that since I've got two real different solutions, therefore x is something e to the mu x and something e to the minus mu x, because that's how you do it when you get two different real solutions. All right. I'm doing the Louis-Sturmville bit here. I should point out that there are times in, say, Maple TA questions where they put a plus in this spot instead of a minus, and that makes a difference, and you have to keep track of the fact that it's a minus, so that when you go back, so that k being positive or negative will be the lambda being positive, negative or positive. So just be careful with that minus sign there. Okay, so cool, that's where I'm up to. And my initial conditions involve x dashed, so I'm going to do that. So the b will still be there, e to the minus mu x, but I'll times by the minus mu. So that's my derivative. Oops, sorry. And my initial conditions say that x dashed of 0, which is a mu e to the 0 minus b mu e to the 0 is supposed to be 0, so a mu minus b mu is 0. So I can get from that a has to be equal to b if I want. And x dash 2 pi is a e to the 2 pi mu, no, sorry, a mu minus b mu e to the 2 pi mu, which is also supposed to be 0. And now I have two equations and two unknowns. I mean, technically three unknowns because I don't know what mu is. But let's look at this. I have a times, the unknowns are the a and the b, that's what I want to find. And I have a times stuff and b times stuff, but it's different stuff. This is a minus 2 mu, by the way. Yep. But it's different stuff. And so it should be possible to solve it. And in fact, if I turn this into a matrix, I could solve it using, row operations. I could also solve it using traditional multiplying other equations by constants. If I multiply this equation by e to the 2 pi mu, like that, then if I go this equation minus that equation, I'm going to get that. So I'm going to go equation 1 minus equation 2, and I'm going to get that. B times minus mu e to the minus 2 pi mu minus b times this, and I bring the b out and I get this. But look, this number is not 0. Because this is a minus 2 mu and this is a plus 2 pi, minus 2 pi mu and this is a plus 2 pi mu. So these numbers do not cancel out, and so I can divide by it and get b equals 0 and sub that back into the first one, and therefore a equals 0 as well. If you're very sure of yourself, you can, upon doing this, observe that this equation is not a multiple of that equation, because it's not multiplied, the b mu and the a mu are not multiplied by the same thing here. This equation is not a multiple of that one. And so since the equations aren't multiples of each other, when you do the row operations, it will come out that a equals 0 and b equals 0. Anyway, but that's just the long version for you. And so therefore, x is, in fact, 0 times e to the mu x, and 0 times e to the minus mu x. So it's just the 0 function. And the way that we indicate that it's always 0 no matter what x is to put a triple equality there, like a equivalent to. So we don't get any non-zero solutions here. Okay. Last possibility is that k is negative. Now I should point out, if there had been a minus in a different spot, then when k is positive, it would have been k is minus mu squared, and I would have gotten plus or minus mu I when I did the square root. So just because k is positive, it doesn't mean you're going to get 0 here. K is positive may actually mean that you end up with complex number solutions. Just pointing it out. So k is negative. So it's negative, and I'm going to have to square root it anyway, so let's call it negative rho squared. Since rho is the next letter after that doesn't look like something else. Oh wow, okay. I'll just keep going. You can leave if you need to. So lambda squared is k, which is minus rho squared. And so lambda squared, lambda is plus or minus, lambda is plus or minus, the rho will square, rho squared will square it to get a rho, and the minus will square root to give an I. Now this is 0 plus or minus rho I. That's the Greek letter rho. It looks like a P, but I'm feeling like using Greek letters today. So that means that my x is going to be something e to the 0x cos rho x, because the real part goes with the e and the imaginary part goes with the cos. You may not need yourself to put the e to the 0x in. I personally need to, because it matches with what I do in Maths 1b. So that's just a cos rho x and b sin rho x. There is no good reason to put the a with the cos or the b with the sine, except that I always put everything in alphabetical order. So a and b are in alphabetical order, cos and sine are in alphabetical order. Yep. And also, and to be fair, I will also go a as the constant and b as the thing attached to the x. That's important if you're going to put a with the coses and b with the sines, because cos is an even function and so are constants, and sine is an odd function and so is x, and so you should make the letters match up because it makes life easier for you. Well, it makes life easier for me. Might not help you at all, but it works for me. Okay. And so that's where I'm up to with that. Again, I'm going to use my initial conditions. X dashed, I'm going to need to figure out, okay, so the a is a constant, so it's still there. Cos becomes sine, only it's minus sine. And I'm going to have to times by that rho because I differentiated. The b is constant multiplied on, so it's still there. The sine becomes cos. And it's not a, and because of the chain rule, the rho comes out. Okay, and x dashed of 0 is minus rho a sine 0 plus rho b cos 0. Oh, yes. No, that's fine. Okay. And sine of 0 is 0 and cos of 0 is 1, so I get that minus rho I get rho b equals 0. So that's 0, that's rho b, and the answer is supposed to come out to 0. Now, rho is not 0. I said that back here, just there. So therefore I can divide by it and I get b equals 0. So in fact, so actually my x is just a cos rho x. And my x dashed is actually just minus rho a sine rho x. Right. Now my other initial condition is that x dashed of 2 pi is 0. So x dashed of 2 pi is minus rho a sine rho times 2 pi. And this is supposed to come out to 0. Now here's the thing, I'm looking for non-zero solutions. In the middle bit where I had my k being positive, my non-zero, it was impossible to get non-zero solutions. When I subbed in my two initial conditions, it just told me that the a and the b were both 0. But in this case, I can choose. And I've already know that the b has to be 0, but there's nothing that tells me that the a has to be 0. So for non-zero solutions, let's say that a is not 0, and so that means that I can divide by the a and the rho, and I just get sine of 2 pi rho is 0. And that is good, because that's going to tell me what rho has to be. The only way that sine of thing can be 0 is if that thing is an integer multiple of pi. Sine is 0 there on the unit circle. And so I know that 2 pi rho is some multiple of pi. Now why would I not choose 0 pi? Because of course if this was 0, sine would be 0. And that's because I know that rho isn't 0 because I've already covered the k equals 0 case. So rho's not allowed to be 0. And so in fact rho is n on 2. Here's a point where it might be worth being careful. If I had gotten a cos at this point, then that would have been a whole different thing. So I'm just going to point out like an alternate universe where we've gone back in time and the question was different. If this had been a cos, what if it had been a cos 2 pi rho equals 0? Well then, so this is all just in a big bracket. Yes, this is my imagining here. What if it had been a cos 2 pi rho equals 0? And in that case, well, cos is 0 here. And so I'm going to need 2 pi rho to be an odd multiple of pi. I'm going to need it to be an odd multiple of pi. Not just n pi, but odd number times pi. And I'm going to need to therefore specify an odd number. And the easiest way to specify an odd number is to go 2n like that. Two n minus 1 is an odd number if n is a whole number. So when I put in n equals 1, I will get 2 times 1 minus 1, which is 1 pi. When I put in n equals 2, I'll get 2 times 2 minus 1, which is 3 pi. When I put in n equals 3, I'll get 2 times 3 minus 1, which is 5 pi. So I'll get the odd number multiples of pi. Yes?
Do you mean pi on 2?
On 2, yes, thank you. Well done. I do mean pi on 2. Not pi, because that would be sine. Yes, odd multiples of pi on 2. And so therefore I would get rho is 2n minus 1 dividing by the pi, and I'll get that. Now, you may think, well, David, why didn't you put a 2n plus 1? That's just as odd as 2n minus 1. And it's because traditionally you want the n to start at 1. I would focus very carefully on the instructions you have been given, because if your instructions say that n has to start at 1, you'll do 2n minus 1. If your instructions say that n has to start at 0, you'll do 2n plus 1. Because if you do 2n minus 1, it would be negative, and rho is a positive number. Okay, so that's just a little what if for you. It's very useful when you do these examples to not just look at the example you're doing, but say, well, what would happen if it was different to that? Surely it would be possible to get a cos in that spot. What would I do then? And if someone asked me that in the Maths Learning Centre, I would be so impressed. not so impressed to give you a prize, but just impressed. So, but I would probably shout out, "That's so cool!" which is what I usually shout out in the Maths Learning Centre. So I love it when students ask me that sort of questions, a what would happen if question, because it shows me that you're thinking about beyond the examples you're being shown. And that is exactly the sort of thing that your lecturers want you to do. Right, and so I have now figured out what the k is. It's n on 2. Well, actually it's not. Rho is n on 2. K was minus rho squared. And so the k is actually minus n on 2 squared. And not just that, I know what my x is as well. X was a cos rho x. Now, final step. I have now found all of the functions. Sorry, I will put that down in a second. I have now found all of the functions that satisfy that original differential equation with constant coefficients. This one just that one just there. I've found not just the k's but the x's that go with them. But these are not just here for show. I'm going to be using them later and combining them with a t, a capital T, to make more functions. So I don't need this constant multiple out the front. I don't need that. And in fact, if I don't need that constant multiple out the front, then this a that we got back here, this a here could just as easily have been a 1, because I could multiply it by whatever I want. And actually, any multiple of any of these functions would work perfectly well, because this is a homogeneous equation. It's equal to 0. So homogeneous equations make subspaces, and we're looking at subspaces of the vector space of functions here, which is awesome. And so we don't need that constant, because either we're thinking subspaces, and when you do subspaces you don't do the constants anyway, you just pick the vector, or we're thinking we're going to use this later and we're going to get more constants from the other differential equation for the capital T, so we don't need the constants. So we do not need that a. That's all I'm saying. So my eigenfunctions are x equals cos n on 2x. I don't need the a for n equals 1 to, well, 1 and onwards. And also x equals 1. Remember that I had an a earlier? I'm going to not have a constant, it's a times 1. Now here's the really, really clever bit. When cos of 0 is 1. And so this is the same as cos of 0 on 2x. So actually it turns out that my eigenfunctions are cos of n on 2x for n equals 0, 1, 2, etc. Yay! Ah, and we put an n there just because. And the eigenvalues that go with this are k, or if you like, lambda. So if you like, you can call this lambda n if you like, if you really want to. So this is sort of the Sturm-Louiville problem sort of sorted out. That's how you get the eigenvalues and eigenfunctions. And this is only half of solving that partial differential equation, which is why in exams they often do this bit for you. Okay, in exams they usually either they'll ask you to solve the Sturm-Louiville thing, or they'll get you to do the other bit, but they usually don't get you to do both. It is not impossible to have to do both. But please be aware when you look at these things that they may have done half of it for you, because you do not want to spend the amount of time I have spent doing this, doing something you don't have to do in your exam. That's you would cry very hard. Okay, that's the beginning. I'm going to keep talking because I'm not going to not finish this now. So here is where I am. If this had been a sine, I wouldn't have had this thing happen. If this had been a sine here, then it's probably guaranteed that over on the other side, I would have gotten 0 and 0 for both the a and the bx. So, yeah. Okay. Right. Excellent. We've done that bit. We've focused on the x, and we're going to go all the way back to here. I've lost a page. Just give me a minute. All the way back to here, we've done this part, that bit there. But we have to now deal with this bit. So now we're going to focus on the t. So we had that. So we've dealt with the bit that would involve x, which was this bit here, and now we're going to do the bit that involves t. But we have an advantage over the first time we did this, is that we know what k is now. We've figured out what the options for what k could be, so we can sub that in. Brilliant. Yep. Okay. So here we go. That one there. And look, this is a second order differential equation with constant coefficients again. It's another one. It's a second order D with constant coefficients. I can do a characteristic equation for it again and see what we get. Lambda squared equals minus 49 n on 2 squared. Alright. And if I solve that, it will help me to figure out the solutions. But I have to be careful. If n is allowed to be 0, I have to split it into two different cases just like I did before. Either n is 0, in which case we get lambda squared equals 0 and we get a repeated solution, or n is not 0, in which case we get two imaginary solutions. So we've got two possibilities. So either n equals 0, in which case we get lambda squared equals 0, because it's minus 49 times 0 over 2 squared, which is 0, which means we get lambda equals 0 and 0, and my t this time is a plus bt. Just skipping some of the working. I won't skip the working, that's bad. E to the 0t plus bt e to the 0t. Because everything's in terms of t now. Okay? I don't have any initial or whatever conditions to deal with this yet. I'm not going to deal with that now. I'm in a different part of the working. I can't use my other boundary or initial conditions until after I've joined it together to make the u now. I'm going to, because this went with n equals 0, going to put zeros on these. Because it went with n equals 0. And when n is greater than or equal to 1, lambda squared is minus 49 n on 2 squared. And so lambda will be, square root of 49 would be 7, square root of n on 2 squared would be n on 2, and the square root of the minus 1 would be I. Plus or minus. And so again, we have two complex number solutions. And so we get that t is a, well, it's an n, a e to the 0x cos 7n on 2x plus bn e to the 0x cos 7n on 2x, sorry, sine. I don't need the 0x's, but I'm just chucking them in because I feel better. All right, so now I have found out what the capital T's are. Sweet. Now, to be fair to myself, if I didn't go back and do this trick where I actually said that n could be 0, I wouldn't have gotten myself into this mess back here. I would have just got either the lambda is 0, which goes with the other one, or lambda is equal to these other numbers, but whatever. I'm just following the sorts of things your lecturer does. And so there I am. I have now figured out what the x's are. I've now figured out what the t's are. This is t0 and tn here. They're labelled by which n we're up to. Okay. So now I can create the u's. Or thetas or whatever they're called. So the u like that. And each value of n, I'll times the x that goes with that n, with the t that goes with that n. And that will give me a particular solution for un, well, a general solution, and I'll add them all up. I'll add them all up, so I'm going to get infinitely many of them. So, the first one, when n is 0, is different to the others, so I'm going to have to do that one separately. So let me just do this. u0 is x0 times t0, and x0 was cos of 0 on 2x. As I recall, what is my x? Yep, cos of 0 on 2x. And my t0 was a0 plus b0t. But cos of 0 is just 1. Like that. And my un is my xn tn, and my xn was cos n on 2x, and my tn was an cos 7n on 2. Sorry, these are t's. Always do that wrong. Back here, they're not x's, they're t's because they go with the capital T. Sorry about that. Should have eaten something a couple of minutes ago. Right, and now I add them all up, so there's going to be this infinite sum. That's the making the u. But it just might be easier for me to separate this one out, so I don't have the brackets. So I have cos n on 2x, cos 7n on 2t, and bn sine, cos n on 2x, sine 7n on 2t. So to bring that inside the brackets. That's just going to be a little easier for myself. So I'm now going to add up all these solutions. So actually the u is my u naught plus all these solutions and n goes from 1 to infinity plus all these solutions like that. Your lecturer may possibly be the sort of person who puts a sum up here and just leaves it with the brackets. I was that sort of person until about 2 hours ago when one of my Maths Learning Centre staff said, hey, why don't you separate it? And I went, oh, that's so much nicer. And it did. It made it. It's beautiful. It makes some of the other things a little less confusing and less chance of losing minus signs and stuff like that. And so here we are. That is what U is. And now finally I can use my final boundary / initial conditions. I think I understand the difference between boundary and initial conditions now. Initial conditions is when t is 0, everything else is a boundary condition. It took me 4 years to figure that out. Don't know why they just don't call them all boundary conditions, but you know. It wouldn't be real academia if you didn't have some sort of confusing terminology that would make you laugh at people who didn't know it. So we use our boundary conditions. So this says that u of x0 is 5 cos 5x. So that's saying I sub in t equals 0. So u of x0. So when t is 0 here, I just get a0. And when t is 0 here, I get 1. And when t is 0 here, I get 0, because sine of 0 is 0. Like that. Just for completeness' sake, so you can see what happened there. So this bit doesn't really exist. Okay, and this is supposed to come out to 5 cos 5x. Right. Well, we're just going to equate the coefficients of cos n on 2x. Some people will do this in the following way. a0, a1 cos a half of x plus a2 cos 2 on 2x plus and keep going until they find this one. A 10 cos 10 on 2x. This is the one that's going to come out to cos 5x when n is 10. That's x is not down the bottom, it's here. Okay, so that's the one, and then there'll be more after that, like forever. But the thing is that the only one that matches with what it's supposed to be equal to is this one here. That's the cos of 5x. And so what I get is that a10 is 5. Because this one doesn't have a matching constant term. There is no cos of a half x here. There is no cos of 1x here. And so on. I've got a10 has to be 5. And an is 0 for all the other a's. For all other n. It may be that I would be given 2 of these, like cos 5x plus cos 8x, and then there'd be 2 of them that come out to be non-zero. So it turns out that actually my uxt, let's just go back to here, the a0 is actually 0, and all of these an's are 0 except a10, so it's not really of a sum of infinitely many things. It's just the 10th one. So we've got B naught t plus just n equals 10 for the a's. So that's a10 cos 10 on 2x cos 7 times 10 on 2t plus the rest of the b's, because we didn't find anything out about the b's. So just for completeness' sake, let's see, that's b naught t plus a10 was 5 cos 5x cos 35t plus all the rest of this stuff. Yes.
You say at the top there, A of n equals 0 to all other n.
Yep.
Why do you say that?
Because none of the other n's give me something that matches with this.
Okay, so if it was sine, like sine of 5x, for example, would you say n equals 1?
If it was sine of 5x,
Yeah.
then there would be no solutions.
Okay.
And we would have done something horrifyingly wrong back there. Yeah, it's impossible. If this was sine of 5x, since these are all causes, actually you can make sine out of cos. You need infinitely many of them, and so you'd have, yeah. So yeah, if this was sine 5x, all of the, most of the a's would be not 0. There'd be some crap that would get smaller and smaller. Yeah. Actually, no, you can't make sine out of cos, because cos is an even function and sine is odd, so it's crap. Yeah. If this had been a sine 5x, you would have gone, I've done something wrong. Yeah. I'm sure there's a way of dealing with it if you were doing this not in an exam, but I don't know what it is. Right. We're nearly done, nearly there. And, yep, okay. You'll be grateful if I miss my train for this, please. Okay. So the last initial condition, so the other boundary condition is, no, it's an initial condition. The other boundary condition is when the derivative is about the derivative, so I'll calculate the derivative, ut(xt). So the derivative of that is b naught. The derivative of that with respect to t would be the 5 cos 5x will still be there, and the cos will become a sine, but I'll have to times by the 35 as well. And the derivative of this, the bn will still be there, the cos n on 2x will still be there, the sine will become a cos, but because of the chain rule I have to times by the 7n on 2 that's next to the t there. Alright, and utx0, yep, utx0 comes out to, when sine is 0, that's 0, so this one's 0. Bn cos n on 2x, cos of 0 is 1. So that's what I get when I sub in 0 for t, there. And this is supposed to work out to be equal to 18 plus 3 cos x, according to the other page. All right, well, let me do the same trick I did here and write this all out. So I've got b0 and b1 cos 1 on 2x times 7 times 1 over 2 plus b2 cos 2 on 2x times 7 times 2 over 2. Aha, that's the right one. Cos of 2 over 2x, that's the same as cos x. This is the one that matches. Now, if this had been like a 15x, I would have had to put some dots and go a bit further. Okay. So, this b naught must be 18. because it's the constant term. B1 isn't there. There's no cos half x there, so that one's 0. B2, well actually B2 and this constant here together is 3. The constant attached to cos of 2 on 2x, which is cos of x. The constant attached to cos of x, this constant here is 3. So it's actually not that B2 is 0, but that B2 times 7 times 2 over 2 is 3, which means that B2 is 3 on 7. And then none of the other b's even appear in this. There aren't any other ones, and so Bn equals 0 for all other b, all other n, sorry. Okay, so we've got the B0 and we've got a B2. Okay, so I've now finished the u of xt, which is here, that thing. The u of xt is there. B0 is 18. I've still got my 5 cos 5x, my cos 35t from the a's. And the only one of these that actually exists is when n is 2. So I've got b2 cos 2 on 2x sine 7 times 2 on 2t, and the b2 came out to 3 on 7, yep. Seven cos x sine 7t. There we go. There you go. That's it. Yay. Sometimes they give you some other ones. But that's pretty much the deal as far as I know. My limited experience of Eng Maths IIA is helping, 8 years of helping you students do it. So I can only experience things that have been asked in past exams, basically. And that's what I've got. Thanks, guys.